I have with me Vedanta Chaudhary, who is basically a director in FUMC engineering. Vedanta has over 20 plus of years of experience in semiconductor industry. Also with him is Shyam Gupta. He also served as director SOC Design and FUMC engineering of NXP Semiconductors. Along as with Vedanta, Shyam has 25 years of experience in various roles in NXP Semiconductors. So I welcome both of you on this forum, Vedanta and Shyam. So you will start.
Thanks, Akhil.
Thank you, Akhil. Yeah, good afternoon, everyone. I am Vedanta. And first of all, let me express that I'm extremely privileged to be able to reach out to all of you through this forum and share some of our thoughts on this important subject of SOC Design Flow. It is also my privilege to share the stage with someone like Shyam, who is a very respected leader in this field with lots of experience behind. I'm also extremely thankful and privileged for NXP Campus Connect, which is led by our NXP India Vice President and Country Manager, Mr. Sanjay Gupta, for giving us this opportunity to share some of our thoughts and experiences on this subject. And thanks to the entire NXP Campus Connect's core team. So without further ado, let me first set the context of today's presentation and the agenda, what we are going to share with you. So first of all, as you know, this NXP Connects Campus Connects initiative is an initiative to reach out to the fraternity of academia mainly, whether it is faculty members or students or young engineers and aspiring semiconductor professionals. So as we proceed through these webinar series, you'll get to know more and more at length on various deep dive topics on this field. So since this is the maiden session today, we thought it would be great if we can cover a breadth of topics to cover the end-to-end design flow that we folks employ in the SOC design side of the story, so that you can have an overall perspective of how things work. And of course, the subsequent sessions will also pick up specific topics and share more technical insights going forward. So that is the inspiration behind this session. There is another inspiration behind this session, and that is the fact that when we ourselves imagine ourselves 20-25 years back in your shoes, when we were fresh engineers, what would be that dream presentation that we would like to go through, so that it gives us a quick start, starter to our careers and some informed choices we can make into where we can invest time to develop our skill set, so that we can be valuable for this industry. So we also try to keep ourselves in those shoes before kind of designing today's session. So that's pretty much the context. I think without further ado, let's go ahead with the presentation itself. So I would request Shyamji to move to the next slide, please. So as you can see, the title of the first section is the anatomy of the SOC design itself. So I have chosen the word anatomy on purpose because unless you know the entire body of work here, the entire value chain, it is probably difficult to also connect on what we are speaking in the more advanced part of the topics. So first of all, as an icebreaker, please connect with this overall picture. So at the end of the rightmost part of this chart, you can imagine yourself or myself or each of us on this call as the end consumer. Whether we are buying a car, whether we are buying a piece of mobile device or any electronics enabled device, we are the end consumer. I have picked up an illustration from the automotive industry, but this is a scalable model for any say engineering context in the semiconductor space. So whichever is the end device, there is always an OEM or an original equipment manufacturer behind that, whether it is a piece of mobile or a car or any electronic gadget. But to get that end device into your hands or get that steering wheel on your hands, I think there is a full value chain behind which creates value towards our consumption as consumers. Whether it is the tier 1 suppliers, which you see the next block, which is essentially I've given one representation of a motherboard, but essentially you can imagine that somebody is supplying all the semiconductor chips which go into designing this motherboard, which will eventually probably enable one of the applications. Then each of those components on the motherboard, if you now left shift to where NXP is written, it could be any semiconductor company for that matter. They would be chip providers or component providers. whether it is NXP or ST or TI or Infineon or Intel for that matter. These are the kind of semiconductor houses which provide semiconductor components which go into enabling the the motherboard that is there. And then we guys here, when we say we mean the semiconductor design houses, and that's the focus of our subject today. We also are consumers of lots of enabling technologies. Primarily, if we pick up one which is very much pertinent for all of us, it is the EDA vendors who supply us the electronic design automation tools to do our computer-aided design enablement, basically to make these chips and design the chips. Then, if you see on the bottom, there is a blue box called the pure play foundries. So, because increasingly semiconductor manufacturing is becoming a highly capital-intensive business, so there are specialized shops. I'm using the word shops, but the factories, I would say, where these semiconductor components get manufactured. But they are extremely integral part of this value chain because there is a very close connection between the recipe which comes from these pure play foundries versus what we design on CAD. So this is extremely important for you guys, whether you are a faculty member or a student or an aspiring engineer, to understand this end-to-end value chain. Because sometimes we tend to, from my experience, I can share that with limited knowledge or limited lateral exposure, we tend to glamorize certain areas where we want to focus our career on, and de-glamorize some other areas where sometimes we have a blind spot that there could be an opportunity to add value. And with our skill set and with our aptitude and attitude tuned in those directions, we can really build up a very successful career and skill set going there. That is why it is extremely important that we understand the end-to-end value chain in semiconductor design. Now, if you move to the next slide, Shyamji, we will double click on the first part, which is the computer-aided design part. Yes. So this is driving home. That's the larger umbrella that we show. Now we are kind of zooming into what makes sense to us as engineers. So if we double click on this computer-aided part, on the right-hand side, what you see are the various areas which go into making a semiconductor chip possible. Now, within that blue boundary on the right, you see two gray boxes on top and bottom, which is called foundry. As I said in the previous slide also, we are extremely in lockstep with this foundry business because that is where the real recipe of manufacturing comes to us from. So, and eventually also the devices will get manufactured. The semiconductor components will get manufactured with these foundries. These foundries typically are companies like TSMC or UMC and the likes of those companies or global foundries for that matter. So now, what do we do? As a first step, we need the recipe. If you can imagine this foundry as a kitchen of your house, right? The chip gets cooked in this kitchen. So it's important to know the recipe of the kitchen to dole out the dishes. So this recipe gets codified in what we know as a process design kit. I will talk more about it later. For this slide, just remember that we are very closely connected with the foundry. We need the recipe of the foundry, which is codified in the PDK. Using this recipe, we have to start preparing our dishes. The first dishes that we need to prepare are the basic building blocks of any chips. Whether it is a standard cell library, whether it is some IOs, some foundation blocks, whether they are embedded memories or analog blocks such as PLL, ADCs, DACs, etc. This typically comes under the umbrella of full custom design. Why I am saying so, you guys as fresh engineers need to know which are the various possible pockets where you can add value. Where does your interest lie? If you like device physics, for example, probably the right place to be is in the PDK world. If you like circuit design, CMOS circuit design, probably the good place to be is in the full custom side. Similarly, once the full custom blocks, the basic building blocks of this dish are prepared, now it's time to prepare the dish. Now this dish is prepared in the semi-custom design world. What does semi-custom mean? Like full custom? There is semi-custom because semi means there's already something provided to you. Maybe you have the basic brick and mortar to build the building. Now it's your job to assemble this building. So why this perspective is important? Because each perspective brings along with it its own set of challenges, technical challenges, as well as the knack to solve those technical challenges, which are also opportunities for all of us. So in the green box here, semi-custom design, essentially we talk about all that is about RTL, about DFT, about verification, about emulation, and physical design and sign-offs. Don't worry, we will talk more about it. At this slide, you should know only the very high-level baskets where you can all focus. Then whether you are doing full custom design or semi-custom design, you have to be very well equipped with a methodology framework. Methodology means a flow sequence or a way of doing these designs. Again, we'll cover more about it, don't worry. But there is also the area of methodology, which in itself is a discipline. If you are a methodology engineer, you are a methodology engineer. You need to specialize in methodologies. The world-class automations, the world-class way of doing our full custom and semi-custom designs. So that is another world where people can focus. Then once your chip is down, what we typically call as a tape out. Once we have taped the design out of CAD, from CAD it goes to mask preparation and the fabrication. So once for that, before that happens, that wafer has to go into a package, right? Before it can be assembled in a motherboard, for example. Now that package design also happens in the CAD world itself. There are tools which help us to make a package code design together with the semiconductor component along with the package. Right? So that part is another discipline in itself. You cannot be a jack of all trades and master of none, right? So you have to focus where you want to invest your energies and skill development. And we will talk more about each block going forward. Once this part is done, then we send this design to the manufacturing house, which is the foundry again, for the mask set preparation and printing this design on what we call the wafer. Right? So this translation of a CAD design into a silicon design happens in the foundry. So once this manufacturing job happens, the chips come back to a semiconductor house for its testing. That means post-silicon testing, which means have you got a component that you had intended to design, right? For post, and this is where the orange box of post-silicon validation, testing, and qualification comes up very pivotal role. So each of this block, the only message that I want to give you here is do not glamorize or de-glamorize any of these fields. Each of those blocks is like the 5 fingers of our hand, right? Each has its own role to play. So similarly, all these blocks are very, very important for all of us to master and specialize so that we can together form a very good machinery. So with that context, let's maybe take one step forward. Shamji, if you can move the slide to the next box, please. Yeah. Yes. So this is again more of a marketing slide, but I have incorporated it here. Why? Because again, the message is very strong. Over a period of time, there are some waves which come, which are trends. For example, there was the trend in the several decades ago about mainframe computers and mini computers. Then it started to be about PCs, and then more recently it became cell phones. And as we speak, the gray graph you see is about the artificial intelligence, Internet of Things, machine learning, edge processing, and stuff like that. Now the point here is, irrespective of this waves will come and go, right? These are all for us to take opportunities from and add value. But whichever wave we are on or riding, the fundamentals of the semiconductor design remains the same. Correct. So what we explained in the previous slide, and we will deep dive further in the subsequent slides, if you master those domains, agnostic of the waves, you will be able to add value. Right? That is why it is very, very important to know those things so that you can ably play when the right opportunity comes. And as we speak, it's a great era of artificial intelligence, IoT. Sometimes we get carried away by this jargon. These are may sound very fancy jargon, but in the end, it is all the same things that we have been doing, whether it was a mainframe or a PC or a cell phone or an IoT. We'll speak more about it. But the only message I want to drive home here is end-to-end visibility of the flow is extremely important, agnostic of the wave that you are riding. Next slide, please. So again, this slide is a more of a placeholding slide, but it is for sending again a message, particularly to our fresh engineers and particularly to the mentors of the fresh engineers, whether you are a faculty member or an experienced person, is that it is our also job to guide our students, our aspiring engineers in the right direction of skill development, because we are in a knowledge industry. Knowledge is the key to our success. Now we can invest time, and our knowledge will be a function of the time we invest in these domains. Now, when we come to the semiconductor world, there are so many opportunities. You cannot just jump around from one to the other. Practically you can, but it is also a function of time. Once you have mastered a certain domain, of course, you can always laterally shift to another domain. But if you remember that this jigsaw puzzle is formed by various components, each component is a very, very important part of this entire design cycle. Whether you want to focus on PDK design or library design and analog IP design being in the full custom world, or you want to focus on SOC design or become a methodology expert, or if you want to become an RTL design expert making some digital IPs, or no, if you want to say, okay, I don't care about the silicon CAD part, but once the chip is out, I want to be an expert on the test and validation and qualification and packaging domains, right? So those are those areas. So please be very, very judicious in choosing your interests and map those interests to the domain that you want to address. Believe you me, I mean, the sky is the limit. You will have always lesser time than the opportunities. So it is an excellent time to invest and start somewhere, right, based on your mapping. And of course, you can scale up as you proceed in your right? So what I'll do in the subsequent slides, I'll pick up each of those blocks, right? And then later we'll again try to stitch everything together. That's how the story is building. So far, what you have seen the value chain of the industry. You have seen how semiconductors and CAD plays a role. You have seen what is double-click version of those skill sets on various domains. Now, I want to double-click further on each of these jigsaw puzzle blocks to give you an insight into what goes behind each of those. So, Shyamji, if you can move to the next slide, please. I'll start with the process design kit. As the name suggests, right, it is a kit. Means it's kind of a bag which is coming to you and be given to your hand as a kit, a toolbox, right, which will help you do what? To marry the process knowledge to the design. On the next slide, please, Shyamji, I think we have more details where you can see a PDK engineer. Who is a PDK engineer? The PDK engineer is a very important person because this is a person who is helping us bridge the technology world to the design world, which is the first bullet point on this slide. You'll see some illustration on the left. Those are the the cross-sectional view of the various kinds of transistors which are available. You'll see some illustrations on SPICE device characteristics. You'll see an illustration on DRM, some schematics, and some layout representation in case you are familiar with it. If you're not familiar with it, do not worry. Okay, we'll have enough time to explore. Even on this slide, I'll talk to you about it. SPICE modeling. Let's pick up one by one. SPICE modeling. So every technology has a recipe, right? What we call as the initial profile of the technology, as in how the technology behaves in a certain operating conditions. So this behavior of the technology or this recipe of the technology is codified into what we call as SPICE modeling, where captures the device characteristic, because this is a foundation. It's like a DNA of the cell. If you know the DNA of the cell, you can make the cell and then replicate the cell. But this is the core DNA. This is on the device characteristics from the physics side. Then coming the design rules. When you lay those out, and I use the term lay those out because you make layouts. When you lay those out, there are various levels of masks, whether they are front-end layers like active layers, poly and contacts and stuff like that, or metallization layers from metal 1, metal 2, metal 3, metal 7, and like a stack, right, on the VRs in between. Now these, you cannot just lay them out like anything. Like any discipline, there are rules, because if, for example, if you're drawing two wires, you cannot come too close because there will be some interference and there will be some spillovers or fabrication mismatches and they get a short. They can, at the same time, they should be at a certain distances so that they are yield friendly. So there are design rules. Then there are design for manufacturing rules or guidances where there is a certain corner of the design recipe where if you place your designs, it gives you the maximum yield. So these knowledge from the process side, again, empirical knowledge from the process side, is modelized into design rules and DFM rules for it. Then parasitic extraction. So what we intend and what we get may be different, right? Because you have designed something on paper. For example, you have scribbled the circuit on paper, then you have laid it out. Right? When you laid it out, there are a lot of parasitics which come, right? Whether it is capacitances and interferences between various layers on the device, etc. Now these have to be also modeled, because eventually these parasitics, that's why we call the word parasitic, have to be known. If they're unknown, then we will get something else on silicon unless we are anticipating those at the CAD stages. So parasitic extraction helps you to anticipate end effects because they are fabricated on the chip in a certain way. So those models are also helped in the PDK domain. Then you make your schematics, like you draw circuits on the paper, then you make the layouts and do the physical verification, which means the design rule checks that you are compliant, that there will be no shorts, for example, or there will be no manufacturing defects, or it is also LBS clean. That means whatever you have from a connectivity point of view, whatever you have connected on the schematic is also getting connected on the physical side, right? Otherwise, there will be again a mismatch between intent and result. Then there are EDA tools, as I said. You cannot do this on. It's very good in the good old days. We used to do it only on paper, pen and paper, right? But when you have to use CAD tools, then also there are various kinds of settings which come along. There's a lot of scripting which gets involved. They have to make the technology file. For example, when you translate manufacturing recipe into a design recipe, you have to know how to codify the technical files. All this world is that of a PDK. So again, connect with the beginning picture. In this entire design flow, you are basically bringing the recipe from the kitchen to your preparation ground, which is your CAD environment. So the PDK engineers is a great opportunity if you want to work in this domain, and you have to build certain skills here. You have to be clear about, which is a blue strip on the below slide, bottom of the slide. You have to be very clear about the device engineering. So get your fundamentals right on the CMOS design. You have to be equipped with EDA tools. I know these days, 20 years back it was different. We still got exposure to some of the CAD tools in those days. Today, I know it is even more advanced, which is a great point. But also get familiarized with the leading edge tools which are getting used in the industry, and get your mastery over scripting languages, whether you're doing a Tcl scripting or a Perl scripting or Unix shell scripting. These are very, very important to be able to eventually add value to the automation world in the field. So I think this is about PDK. Okay, again, you imagine my first slide. I'm basically building the block one by one PDK. Now we will go to the next slide, which is full custom design. Shamini, if you can do the next slide, please. Yeah, the next slide again. So, by the way, this topic, sometimes there's a misnomer between full custom and analog. Now, the point is, can analog is always full custom, or digital also can be full custom? I think this is the misnomer I would like to solve it. Analog is essentially what is not digital, which is basically all that, the entire infinite set of points on the signal, right? Whereas digital is something which is sampled set of from the signal. So it is more the type of the design which is getting talked about in digital or analog. Full custom or semi-custom is more about way of working. Whether you are assembling everything by hand, that means are you constituting the cell from the DNAs, or your cells are given, you're only now assembling an organ of the chip, right? So when you don't get confused about that, full custom here means you're doing everything by hand. By hand, when I say from the basic building blocks, the most fundamental components of the anatomy of the chip. So here is where you guys can specialize on doing some library development, whether they are standard cells, which can be inverters, buffers, NAND, NORs, or all kinds of gates, flip-flops, etc. Right? So that's one domain in itself, which needs to be characterized, which needs to be really ensure that they are robust from a quality standpoint. They can withstand the various temperature ranges that the device is expected to perform, etc. It's in the discipline in itself. Then embedded memories, whether it is SRAMs or ROMs, because you know the major part of the real estate of the chip is essentially memory intensive, right? It is very hungry in terms of chip real estate, and you know chip real estate is dollars. It is direct mark on the gross margin or the pricing of the chip itself. So embedded memory design, how can you make the most area efficient memories for the best performances and most optimal leakages and power budgets? So that is the discipline where the challenges from a design side will come for you as engineers to solve. Or IOs, where basically you are marrying the macroscopic world to the microscopic world. How do you translate a high voltage domain into a more microelectronic domain? The transition between the macro world and the micro world is essentially happening by the IOs interfaces. Right? So that itself is, again, it will have some elements of ESD, latch-up. It will have elements of, you can say, some element of analog as well, which needs to go into this kind of IO cell design. Or for that, analog macros, where tuning the circuits in the right centering of the design recipe is extremely important, whether it is a PLL for clocking or it is for data conversion, ADC, DACs, and other blocks, which have its analog design in itself, as you know, will be a challenge in itself that we need engineers to solve. Then complex interfaces that we talk about, and essentially also when we work in the CAD environment, we have to generate different views. For the same design, there could be different views which work for different aspects of the design flow. Whether it is, for example, schematic and layout, when we talk about full custom, is the primary views, but you need an abstract view where you only have the abstraction. That's we say abstract view. Why? Because we have it in an abstraction where we need the pin information only for doing the next level of connectivity on the chip level. So these are the different CAD views which are required to package the delivery or the deliverable for the next level of integration in the chip. So this is the world of full custom design. So we talked about the foundry. We translated the foundry recipe into CAD through the PDK. Now using that PDK, we are making full custom designs. So here, the skills that you need to invest on are CMOS basics, the circuit design, layout design principles, which by the way is an art as well as a science. The more optimal layouts you can make, the most competitive the chips eventually will become. The simulations, the extraction, the physical verification, these are the kind of stuff that you will be doing. And as I said in the beginning, this is the maximum leverage we can play to optimize the PPA when you say performance, power, and area, because these are the fundamental building blocks, right? It's like whether you make a small house or a building, the bricks are the same, right? So unless the bricks are of high quality, your building will not be of high quality. That's the challenge for engineers to solve in this part of the world. Moving ahead, Shamji, to the next slide. Is now we are going one abstract more on the semi-custom, where we are talking of IP design and SOC design. Now, again, even before we move to the next, we can move to the next problem. When we talk of IP design, now the point is many times, again, a misnomer. What is IP? Even this piece of slide that you see is a piece of IP, right? It is an intellectual property, something which is a property of my own from my intellect. So from that point of view, everything that I create is an intellectual property. But in this slide, we are talking about digital IPs, which means the reusable blocks or reusable design elements which get integrated into the larger chip. In the previous slide, when we talked about, those are full custom IPs. Those are also IPs. In a way, in their own rights, they're IPs because they're intellectual properties for somebody who has created. Here, we are talking about digital IPs, which means these are essentially in the domain of the RTL. These are soft IPs, right? These are not hard IPs. Previous ones are hard IPs. This is soft IP, where we are talking of RTL design, where we start talking of behavioral models, where we start talking about behaviors, and when we start talking about the way the functionality gets codified. So there are teams, and then these are highly competence-oriented teams which have to design digital IPs which can be used in the overall SOC. Similarly, there is a subsystem. What is a subsystem? Again, these are words to play around with the different levels of abstraction. A set of IPs together, which is almost like a system, right? In its own, in its more or less complete in its own self, is a subsystem which is reusable. Whether it is this chip or that chip, this piece of subsystem can be reused. So these are the domains that we talk about in the front end environment here, which is the first block on the blue side is a front end. Front end means front end. That means it's like the front end of the design, right? So again, there are I would say often misnomers between front end and back end from the process world. When you talk of front end and back end in the process world, it is about the front end of line, how the chip is getting manufactured in the chip in the foundry, the front end of line and back end of line, where back end of line is essentially the metallization steps. Front end of line is more the foundation layers, the active layers, the polygates and stuff like that, which is more closer to the semiconductor, the fabrication area. But here we are talking of front end and back end more from a handoff point of view. Somebody does the job before the other guy can do. So the guy who is doing the job first is the front end guy. The guy who is doing the job later is the back end guy. So it is a different parlance here from a cycle time point of view or the sequence point of view. In the FE side, we are doing all these digital IP design, subsystem design. Then the SOC RTL integration. Once you have the blocks, somebody has to integrate to make this as an SOC. In the end, you need a device, right? A complete chip. So this integration has to happen. There has to be elements of design for test, because testability has to be built in. It cannot be an afterthought. You cannot be, okay, I have designed the chip, now I'll make it testable. No. You have to make your design testable by construct. So that's where DFT comes as a FE element here. Then once you have assembled your RTL, it's job to do a functional verification. That means once you have assembled your chip, is it functionally behaving the way it should? So that's functional verification. Then maybe once it is synthesized, and you also have a gate level netlist out of it. I'll cover it maybe a little bit later. So then it's time to about doing a gate level simulations. There are aspects of our formal verification and emulation. In the interest of time, probably I will not deep dive at this stage. I'm sure we'll have opportunity to speak about it later. But okay, so this is the front end part of the world. Then the back end comes where, okay, one team has handed it off to another team. Guys, I have assembled the RTL. Now, can you make it physical? Can you make it printable on the wafer? So this printability on the wafer is done by the back-end cycle, where the RTL netlist is synthesized. It is synthesized into gate level netlists, where the real gates, right? What we talked about in the full custom design, the ANDs and inverters and buffers and NORs and flip-flops and everything starts to take their physical shape, right? We are now going one level abstraction below. Then you do a floor planning where basically you do a planning of the real estate. It's like when you are making a house, you know exactly, you have a blueprint of where will be the bedroom, where will be the kitchen, bathroom, etc. Is the blueprint here, right? The floor plan is a blueprint of the chip to be. Okay. Once this blueprint is done, which is called floor plan, then you go into what we say placement and routing, which is the physical aspect of translating those layouts where the full custom guys had made certain layouts. You remember, those layouts now get printed on these and these tiles, basically those rows, and we'll cover more about it in the chapter section. But the place and route basically happens here. Clock tree synthesis also becomes extremely important, where you ensure how the clock, which is the heart of the chip, is traversing across the entire design in the right way, in the way it should. Then once you have done the physical assembly of this physical design of backend part, then it's time to also run the sign-offs. Sign-offs means in the various permutation and combination, sometimes we also call them PVT corners, because we know when in the physical reality when the chip is getting manufactured, different based on where the wafer is located, where the die is located on the wafer, it could be difference in doping, difference in the way it is exposed to the machinery, etc. Accordingly, the recipe which we had tried to model in the spice, right, in the earlier slide, may vary. So PVT variations may happen. But how do you ensure that your design does not only work in only the typical condition, but also in the corner cases? That is about cross-corner timing sign-offs and other sign-offs as well. We have to take care of the physical verification, just as we did in the analog or full custom side. We have to ensure the physical, the integrity of the signals, right? Because there are again parasitics which are involved, so the reliability of the device from a parasitic world also needs to be taken care of. And then electromagnetic interferences and electromagnetic compatibility, when the chip that you make is assembled by somebody with another chip on the same maybe in motherboard or in the same package, then what are the interferences and the crosstalks which are happening between these two animals which are sitting in the same cage in the zoo? Right? So that's where is EMI EMC come into place. All these sign-offs we have to do before we say my chip is ready for a tape out. I am confident that my design will not only work once, but will work every time, whether you fabricate in a slow corner or fast corner, whether there are interferences or not. Okay? So this is about semi-custom world. So you can imagine the amount of challenges which go into this domain. See, each domain that we are talking about comes with its own set of challenges that needs to be solved. And the skill sets that we need here are, of course, the digital design basics, your combo logics, your sequential logics, the flip-flops, your setup time, your hold time, the state machines. These are the aspects that you need to be aware of in mastering this domain. And then design flow knowledge, because here a lot of automation, a lot of dependence on EDA tools is there, right? So those knowledge will be extremely handy for doing semi-custom. So PDK, you talked about full custom, semi-custom. Moving ahead, now the chip is ready. Somebody has designed the chip. On next slide, please, Shakti. Now, okay, my chip is ready, but before I send it to the fab, I need to anticipate how this animal is going to be caged in the zoo. Right? So I need to model the cage itself. Right? It will be packaging. This is where the world of packaging comes. Now there will be die to package. For example, there would be die means the one unit of that wafer which is cut out by a diamond saw is one die. Right? Now this die has to be assembled in a package, and there will be these gold connectivities for the pins, etc. For example, again these are details I don't go, but this itself in its own way, a discipline in itself, how you assemble the die on the package. How do you do the substrate design? How the routing? You have done a routing in the physical domain where we have talked about the metallization routing. Here we are talking about the substrate design routing. How those have to be routed within the substrate so that it can be rightly printed eventually. Then there are the different kinds of packaging technologies, whether it is a flip chip. Flip chip means you have a chip with the ball, essentially the leads, all right, directly printed over the chip itself, and you just have to flip it and put it on the substrate, and the connectivity gets automatically established. This flip chip. But wire bond was traditionally what I said, right? Everything is exposed, and then you connect the IO pads to the pins with maybe some gold wires. For example, what is being shown on the second illustration here. Then the other thing is silicon in package. Nowadays, what we are doing, just as SoC is there, system on chip. Now we are doing system in a package. That means, can we marry two different SoCs, which in themselves are in their own full rights, completely independent components, and they reside in the same house, in the same cage, right? To have certain performance benefits, and that is packaging word. And we have special technologies such as silicon in package. How do we do two dies together on a single packaging so that they become actually a master component of maybe more than one die together? Then there are special technologies like, now if you have a die to die, how do you connect them? There are technologies such as through silicon via, where you basically there are holes drilled. You can imagine them as holes drilled into the first chip or the second chip, so that they can just be placed on top of each other and they get connected on its own. You can imagine the challenges and the opportunities you guys have. Sometimes when you talk about from your shoes in the university, you might see semiconductor as only doing one piece of the design, maybe full custom or semi-custom. But here out there is an entire world in itself. Do not limit your imagination. I mean, do not limit your thought process as to where you can contribute and add value. Packaging in itself is a domain. So the skill sets that we will need here: substrate design, package know-how, silicon in package specific skill sets, etc. I know we cannot do justice to all these topics in 2 hours. That's why this is just a curtain raiser session. You can go back with the jargons that you are picking up from each slide, read up more about those, because that reading will be very important, whether you're facing an interview, whether you're preparing yourself for the next career. Those reading will always be of useful for your entire career. So please pick up these jargons and pointers and read up more once you leave this session. Moving ahead to the next slide, Shamji, please, which is about test engineering. Again, now the chip has been packaged. So we had PDK, we had full custom, we had semi-custom. After that, we had the package design. Now it is somebody has done the finishing job and given it back to you. Guys, you had ordered this part. Here is the part. Now do what you want to do. Now what we have to do is to test it. Basically, the requirements that we had in the original intent of the architecture. Why we had designed this chip, right? We had designed this chip for a certain reason. Now, and we have to validate this chip against those reasons, against those intent. This is testing, where you have a device or a circuit under test, which is on the blue box there. Okay, and then you have a certain set of stimuli that you supply, and you know what is the expected response. And again, I know this is a very layman way of understanding it. Please understand, this is going to be in itself a PhD topic, right? In itself an area where you can make your entire, I don't know, 40 years of career in itself, right? So test engineering is such a discipline where we talk about functional validation. Is the chip now getting functional on silicon? You had great performances verified on CAD. Is the same performance coming also on once the guys or the devices get manufactured? Then the automated test equipments, that is ATE, right, where there is a lot of characterization which happens of the various operating parameters, and then qualification. What is the difference between test and qualification? Test is you ensure, okay, the functionality is correct, it is working, the samples that I am getting are working. Qualification means, will it last for 10 years or 15 years of my device lifetime? For example, if you have embedded a chip into a vehicle, you know this vehicle has to run safely and securely for at least 15 years. Now, in these 15 years, this vehicle will go through so many kinds of conditions: hot temperature, cold temperature, rough roads, everything, right? So in this robust testing has to happen, where you are ensuring the reliability of the device, right? The reliability of the device, that it will not only work once, but every time, every year, throughout its lifespan. That is qualification. Now, again, as I imagine you might find this very philosophical at this stage, but believe you me, these are examples or fields where you can really specialize. I think that's more or less, if you remember my first slide with the blue boundary, the PDK, the full custom, the semi-custom, the packaging, and test. Now we have covered entire things on this, at least under table of content view, right? If you read a book, you open first, you go to the table of content. We have gone through the table of content. We know what each chapter is having and what you need to know to master this chapter. That's the purpose of the first few 40 minutes we have spent almost of this lecture. Now we'll start to add a little bit more before we deep dive into each of those further, so that you can now go into each of the chapters. We'll also cover 2 or 3 more points, because without that we cannot complete this picture. before we start to do that. So if you can move ahead, let's jump on the next slide, please. Now we talk about design methodology. Now all that is fine. So far what we have discussed is design. What is SOC design? What are the various baskets and elements that go into SOC design? Now we talk about methodology. That means how do we do this job, right? Now, any device that we are working today for the industry is inspired by the smart world. This slide, by the way, has no relation to Soc design, but this is important from a context point of view. You guys have to know that you are creating solutions for a smarter world. We are making our world smarter with this electronics that we are all building together. So what is a smart device? I mean, if you and I claim ourselves to be a smart person, we have the ability as humans, smart humans, to sense with our sensory organs, to process, think. Then if we need to connect with others to also get their guidance and viewpoints, we connect or get more knowledge from the internet. And then finally we act. Same way, a device, also a smart device, will have to be able to have sensors to do sensing, then processing, then maybe connecting with Wi-Fi and other technologies to other nodes, and then eventually actuating or within some actuators. And whatever they do has to be secure and safe. What do we mean? Safe means it has to be safe to be, if I am riding the vehicle, I have to be safe within it. And also the vehicle has not to harm anybody else on the street. That is safety. Security means the component has to be safe from me. Right? You see the duality of that. I have to be safe from the device, and the device has to be safe from me. That is security. That means I will not have any loopholes in the device where there are security or vulnerabilities that I can compromise the quality of the device. So that is security. Whatever we make as semiconductor components, our design methodology has to ensure that we are building the smart blocks with safety and security. That's why this slide is very important so that you have the lateral viewpoint when we are addressing design. On the next slide, please. So this again, I have just stolen NXP slide here. It's not an intent to market NXP, but just to say, when we are just to link to the previous slide, sense, think, act. You know, there could be different components. Whether when you see the sense column, you can have different kinds of sensors, right? Whether it is about radars, cameras, or lidars, or motion sensor, pressure sensor, ultrasonic sensors, etc., temperature, light sensors, etc. Or you have processing, where you could have processors, you have microcontrollers, and you have also specialized domain controllers and gateways. Then finally, there will be something which is actuating or taking after you have taken a decision through the processing, you have to actuate it, where you have basically engine transmission, whether we talk of automotive. This is an example from automotive. So about doing some stuff on the AC or the lighting of the car, those are actuations which are happening. Now your design methodology, why we bring these two slides here is, your design methodology cannot be piecemeal. Okay, I'll solve this part of the story, but I don't know about the rest of the story. It has to be an end-to-end story telling here. Right? So now next slide, please, Shamli. Now this is why you should also be cognizant of the fact that there are different design types. Okay? SOC design, although the topic today is SOC design flow. I mean, SOC itself can be different flavors. It could be a completely large SOC or digital design, or it could be a digital-centric mixed signal design where it is primarily digital, but you have substantial amount of analog components. Or the third one is analog-centric. The chip itself is analog-heavy or analog-oriented, but it does have some digital content as well for doing certain control aspects and processing aspects. And finally, a completely RF design where you have an analog front end, a radio basically, where it is a complete in itself discipline in itself. Now, which are these, around these four pillars? There could be the flavors could be different, right? Whether it is, for example, when we talk of SOC or digital centric, we talk about system design, we talk about digital RTL to GDS, we talk about the advanced CMOS effects. Moment we start to talk about, you can say the moment analog starts to happen there, it starts to have AMS sign-offs as well. When we go to the third pillar, which is analog centric mixed signal design, there it has to be analog design and verification, analog assertions in digital verification, analog digital co-design aspects, right? These are methodology topics that we have to address. And then when it comes to RF design, it's completely a discipline in itself, where we have RF design and verification, where we have frequency-based EM simulations or SIP issues getting models. So we have to have design methodologies which cater largely to the associate design cycle, but also which addresses the specificities of each animal that is listed here. Okay? So we should have the right design flows to support all that. So this is from the methodology angle. Again, why I'm saying this is because you guys may also choose careers where you focus on design methodology specialization, and you have to cater to the specificities of each of these design methodology domains that we have talked about. Next slide, please. Okay. Now again, I'm conscious of time. I think I'll try to conclude in the next 5 minutes. So basically, why this slide is important, and we bring it here connecting to the methodology area. And I think I have just 2 more slides before we deep dive again into some of the specifics with the help of Shamji's lecture. But this slide is important because increasingly we see people are using these jargons, IoT, Internet of Things, or connected world. I mean, all these are jargons. To me, in the end, these are all components which are connected. Even today's vehicle, the smart vehicle, and it will be more and more smarter as we proceed, is nothing else but an IoT node. In the end, it is a part of the connected world. So the classical way of architecting the vehicle, which used to be highly mechanical centric with some electrical components, is now getting flipped. The vehicle design is becoming like a cell phone design, where you have the vehicle as an electronic design, top-down electronic design, where you have, instead of a distributed approach, where okay, I plug in some electronics here, I plug in some ECU here, etc., etc. Now, no, it's a correct by construct thought process, and the methodology has to support that, wherein we talk about domains and domain controllers and everything getting integrated with a traffic police sitting on the central node, the gateway that we talk about here as the master controller of the vehicle. So now, with this paradigm shift in the way the vehicle also is becoming an IoT device, like any other device, whether it is a smartwatch, I know I'm trivializing it, or whether I'm wearing a smartwatch, whether I'm using a cell phone or it's a car, in the end, the principles remain the same. So your design principles, your design methodology focus will have to address this pervasive way of building in automation and integration into the way electronics is designed. Next slide, please, Shabir. Now, a few slides, and I'll be very fast on that. But our design flows must address the solutions. I mean, we cannot any longer be piecemeal, all right? It cannot be piecewise linear. It has to be able to maximize the system level architecture. It is a top-down way of viewing the device architecture, where we have to have the right hardware-software partitioning, right virtual prototyping opportunities, system level modeling. In the end, the car itself will become a model where somebody else, a customer, maybe an OEM or a tier 1, and can simulate it, right? And it is, I'm not saying fancy things here. It is actually demands which are coming. Can you give us a virtual prototype of the architecture that we can emulate at our end, right? When I say our end, it's the customer end, somebody who is assembling the vehicle itself. So these are the kind of opportunities that we have to play around, you guys, and that's a fantastic opportunity for all of you young engineers out there to address solutions played with the right design flow. Next slide, please, Shanti. Then about quality, you cannot just design just for the sake of fun. It has to be robust, as we said. So there are different vectors to talk about, whether it is requirements management. I can spend 2 hours only on this topic. That's not the intent. Here again, I'm just scratching the surface. There is something called a requirements management methodology. You should look up and read up these methodologies. There's something called about DFT. Anyway, we'll cover more in detail in the subsequent slides. DFT, design for test, and also analog reliability. The reliability across, is your device aging? Is there an aging factor which is happening in a device? Does it last through the lifetime of the devices? All these aspects are design influence to cater, right, in the associate design. So this is an excellent opportunity for all of you to add value as engineers. Next slide, please, Shamil. Then the new trends. What are the new trends? I talked about safety and security. I will not spend more time here because each of these are 2-hour sessions, right, on safety and security. But you should be aware that you just cannot be fanciful about doing a design. You have to be fanciful about doing a design which works in all these contexts, whether they are safe, they are secure. Are you able to make designs which are reusable? In the end, you have to make designs which are for the industry in the right time to market. So are your designs reusable? Are your design methodologies reusable? Do you have enough innovation to make path-breaking methodologies for the greatest PPA? And what about the latest emerging trends? What about AI ML? Is it just a fancy word, or I can import the principle into my day-to-day work? Can I make my day-to-day job more efficient by deploying AI ML techniques? Right? Can something read through my log files and predict the way my flow will behave in the next cycle of its run? Right? Or what about RISC-V is emerging as a open source architecture? Am I able to leverage these kind of architectures for doing end-to-end designs? So the design flow has to support all these industry trends which are next slide, please, Shanti. Then functional safety. As I said, I will not explain more about safety. I talked about it, but the safety journey also has been evolving right from early 2015-16 time frame until now, where we are saying that and particularly this is important for automotive designs, because your vehicle has to be safe on road for the passengers and for the people on the pedestrians and other vehicles around, right? So but what happens while the device is while the vehicle is working and flying on very high speed, something in the electronics inside the car goes wrong? Can it compromise the safety of the passengers and the people around? And what happens in that spur of the moment? Can we make it still operational? Can we make it fail operational? Right? And can we actually make it highly dependable by saying that even if a failure occurs, my device will still continue to run? Right? These are the kind of principles that the design flow has to address. And there are different principles here of various categorization of safety compromises possible based on severity of the damage which can happen, based on the exposure that the operator of the device is having, or based on the controllability. Once something comes, is it controllable or not? Accordingly, a big matrix is there out on the right. We can read through more blogs here which are supplied. But idea is there are different safety categorizations which are there, and we have to make our devices compatible to the required standard given for a given application. So please do read up a lot about functional safety, particularly if you want to make a career in automotive semiconductor design. I think my last slide before we go into a deep dive, and the next slide, please, Shamji, which is also about security. Just as we said in the previous slide, probably I forgot to mention, there is a standard called ISO 26262, which is a industry-wide standard which governs functional safety principles. Similarly, there are standards and regulations which are on the security side of the element, which is said as ISO SAE 21434. Again, we will not have time to go and deep dive in these, but there is standardization which is happening as we speak. This is in development. It is, I think the safety standard is a little bit more mature than the security standard, but this is again happening as we speak. It in itself a discipline. So if you want to make a career where you are an expert on security engineering for the devices that you make, you can make a career out of it. So please do read up these fundamentals which go into the design psyche, design thought process, and the design. I think we can move to the next section. I think this is the transitioning slide. Yeah, maybe I'll skip this slide in the interest of time. It is more about security. So with this, I'll take a pause and I will hand it over to Shanti to also give us further insights into some of the design flow. Over to you,
Shanti. Thanks, Vedanta, for a nice introduction and covering the whole landscape and the ecosystem, starting from EDA, to the foundry vendors and the silicon houses, who are doing the product development, which are going to OEMs end of the day. So, good evening, everybody. My name is Shyam Gupta, and I am working as Director Associate Design with NXP for almost 16 years now, and overall 25 years in the industry. So, it's my privilege, to connect with all of you through this campus connect program, and share the information as you guys step outside the academic zone and start building your career in the industry. So I hope this the sessions which are happening through this campus connect program, which will give you the relevant information and will help you make the right career choices going forward. Okay. So next 45 minutes or so, I will be focusing on the SOC design flow. So Vedanta has given a very nice picture about the EDA vendors, and then the different type of SOCs, which companies like NXP might be doing, depending what is an application. It could be full analog or full custom. It could be semi-custom. It could be fully digital, right? So with that as a background, I will be talking about a typical SOC design flow, which is exercised by any silicon vendor, and then see how different steps in the design flow stitches with each other. Okay. So what is an SOC? So depending who you talk to, different people may have different interpretation of the SOC. So there could be one set of people who may say that it's a VLSI manufacturing technology advances has made possible to put millions of transistors on a single die, and it enables designers to put system on a chip that moves everything from the board onto a chip eventually, right? I mean, as the feature size is reducing, we are able to compress more and more functionality on one chip, so this could be the definition which will emerge, when you talk to one set of people. Okay? So similarly, when you talk to, let's say, another set of people B, they may say that SOC is a high-performance microprocessor, since we can program and give instruction to the microprocessor to do whatever you want, right? So similarly, if you talk to the third set of people, they may say that SOC is an effort to integrate heterogeneous or different type of silicon IPs on the same chip, like memory, microprocessor, random logic, and analog circuitry. So you may now connect well to what Vedanta was teaching in the last lecture, right? So ultimately, what is it? Is it SOC what is described by people A, B, or C? So basically, all of the above are partially right, but not very accurate, right? So SOC is all about, what all these three people are saying, people A, B, and C, but SOC is not only these things, but something over and beyond. So let's see what SOC is actually, in the next slide. Okay? So what is SOC? So SOC is not only chip, but more on a system. So SOC is complete chip, software, and integration. So basically, you can imagine if you give a piece of hardware to somebody, it's of no use unless a person is able to write a software on it, and he is able to integrate the software and hardware together for the optimal use, as per the application need, right? So that's what overall an SOC is. So SOC chip includes embedded processor, ASIC logic and analog circuitry, embedded memory. So we'll talk about these things further, in the subsequent section of the slide. So at a high level, any SOC will have an embedded processor. It will have some ASIC logic, the IP blocks, which are implementing some industry standards, let's say on Ethernet or USB or SD card or whatsoever. So it will have quite a bit of analog circuitry to really enable the on-chip clocking, to enable analog to digital world conversions and those kind of things. Embedded memory, so all these SOCs will typically have embedded memory where you can, temporarily load the data from external world, do some processing, and then, you bring the data out of the chip again. So it will have some embedded memory in that sense. So SOC software includes operating system, compiler, simulator, firmware, driver, protocol stack integrated, development environment, application interface, C++ assembly, right? So you can imagine today's world SOC are pretty complex, which may have large number of heterogeneous cores, which are integrated in one SOC with large number of accelerators. So whosoever wants to use the hardware optimally, he needs to be enabled with all the software libraries, simulator, compiler, firmware, so that he can write his application, can map it, in an efficient way, and make the more efficient and optimal use of hardware enabled for his application, right? And C++ assembly is kind of intuitive. People will be writing their application probably in a higher level coding language, and then probably the compilers, the assemblers, and those things will actually translate high level program to machine level language, and then that's how it will get executed by the code. So SOC integration includes the whole system solution, software, hardware combined together, manufacturing consultant, so and also technical support. So these are the complex, hardware products, and it's not intuitive to use, these hardware parts for the most efficient usage. So SOC integration also includes giving the technical support, to the end user, so that hardware and software combined together can be used in an efficient fashion, right? So this is how you. So Vedanta gave a nice description about how, let's say, domains are evolving with time. Let's say earlier there was a flat architecture, but now you have more domain controllers, and domain controllers are connected to each other and making it a kind of IoT node. So here in this slide, I'm trying to give a different view of the end application to the device abstraction level. So let's say as an application, what all of us will see, and the end user is, let's say, an automobile or a handheld device, let's say a mobile phone. And if you go one level down, this application will be divided into different systems, right? So you can imagine Vedanta was showing different domain controllers. So on a simplistic view, you can imagine, each domain controller is represented by, let's say, one system, and each of the system will have, the SoCs or the hardware, getting sourced from different places. So next abstraction level will be the module. So basically, each of the subsystem will have multiple SoCs, and each of these SoC will have several functional blocks, which you can always call as a module, which will be talking to each other. So next one is gate. So once you go deep down inside a module, you will see ultimately it will be millions of gates which are connected to each other in a certain fashion, representing the end functionality. And if you go one level deep, the gate will ultimately be represented, by some transistor level circuits, depending again on the application, it could be CMOS or some other technology. So for this illustration, we have shown CMOS kind of circuit topology. And end of the day, this circuit will get realized on the silicon, as a device in the fabrication process, where the different, mask layers will be fabricated one after the other using a very, very complex manufacturing process. And that's how, you will get silicon end of the day. So, so you can imagine, depending, at what abstraction level you are working, there are different skills needed to excel, in that particular abstraction level. So I'm linking this presentation to what Vedanta, showed in last 1 hour. So these are the different abstraction level, application down to device. Different skills are required to excel at any of this abstraction level, and depending where your interest lies, you can pick any one of them, and then build your career and the knowledge and the information needed to excel, in that space from there. Right? Okay, so now what defines the SoC design flow? So SoC design flow is nothing but a set of tasks which are required to be executed in a particular sequence to ensure that you get a functional silicon which behaves, in a desired fashion. So I'll not spend much time here, but we will see, how a typical SoC design flow look like in next few slides. So, so this is a simplistic view of an ASIC design flow. And when I say simplistic, in actual, there are many other iterations or many other functions, which are coming in the picture, and then there are several loops and feedback cycles, as you go from one design flow step to the other design flow step. So this is just a simplistic view in the interest of time, and giving the holistic information that how an SoC end of the day takes the shape of the silicon, starting from the requirements which comes from the customer. Okay, so basically it starts with the product requirements coming from customer, then it translates into an architecture definition. From architecture definition, you put together an chip RTL in an hardware description language. It could be Verilog, VHDL, or mix of them. Then you want to verify the design to make sure that whatever functionality was intended, from that RTL, you ultimately getting that functionality. Then design for test. So so basically you are enabling certain features in the design so that you can catch the manufacturing defects in-house before silicon shows up, in a customer shop. And then Physical design, so basically translating your netlist, in a layout. So all those steps which are needed in between are represented by a physical design process. Then mass data preparation and tape out. So ultimately, after physical design, your layout will be represented in terms of set of mass layers, and which will keep on varying depending which foundry you are going to and which process technology node your silicon is targeted to. So your physical layout will be represented in terms of mass layers, and it will go to the foundry, and they will process those mass layers in a certain sequence, and that's how the end silicon will come. And after the silicon is there, silicon is too delicate to handle. It has to work in a rugged environment. So that's where it will be. That's where the packaging comes into picture. So there could be multiple type of packages like a ceramic package or plastic package. Different silicon components may be generating, different amount of heat. So you want to have an good enough cooling mechanism, and also, the pinouts from different SoCs are different. So those will be certain other criteria, based on which you will choose one package or the other. So once the package silicon is available, of course, you will go to the post silicon verification, or let me not call the word verification, but post silicon test or the post silicon validation. So this is where you are screening your silicon for any manufacturing defects or functionality defects, or performance or the characterization related defects, in these two flow steps. Okay, so now we will deep dive into these flow steps, one by one, and then see how they are stitching with each other. Okay, so first one is freeze product requirement. So what does that mean? So you can imagine, for any typical silicon vendor, they are supplying silicons in specific, application domains. Like in NXP, automotive happens to be one of the big domains for us. And so basically, in the companies like us, there will be a set of people who are market facing, right? So they are in constant touch with our lead customers, and they are trying to understand what are their next generation product requirements. Okay, and the requirement they collect, from customer is more at an application level. So that's why we are calling it as a market requirement doc. So end customer may say that, okay, today I'm running an car, which where I have to apply the brake manually, whenever I see the pedestrian, right? So in my next generation vehicle, I need a vehicle to apply brake by itself when any pedestrian comes there, right? He may say that today I can run these many audio video equipments in my car, but I want to enable these many new type of devices in my next generation car, right? So similarly, he may say, I want to process, what is happening around through, vision processing engine. So those are the kind of market requirement documents, market requirements, which, the technical marketing folks will capture, in discussion with the customers, understanding their future requirements, right? And then they will translate this market requirement document into something called as product requirement specification. So product requirement specification is abstraction level, one level down, where you are trying to translate, okay, if market says, these are my performance requirements, this is my feature requirement, then as per the standards, let's say on the Ethernet, there are multiple standards evolving. Let's say on the Wi-Fi, there are multiple standards evolving. So they will translate it to a level where they can define a product. Okay, these were the end user requirements, and at an electronics product level, this is how the market requirements map to a product. Okay, and we will call it as product requirement specification, or sometimes we may also call it as a requirement specification. Okay, so once we have the requirement specification, so next, steps which comes into the design flow is architecture definition. So what is the architecture definition? So once, let's say, you have the product requirement specification, so there will be architects, in companies like us, and they will translate this product requirement specification into architectural specification. What I really mean is, let's say there are different kind of cores, which are available. Which are available to be used in any SoC design, right? So now these architects will understand what is the product requirement specification, then decide, what is the most optimal core to be used in a specific product, what is the most optimal interconnect, I mean, how the different cores should talk to each other, depending, I mean, what are the different IP blocks, which should be integrated, in that overall architecture so that it can meet the product requirements. So once the product architecture specifications are ready, then basically translate to actual detailed design technical specification, right? So, so this is further detailing of architecture specification to, you can say, almost at a signal level or at a bus level, right? I mean, here you are defining, the clocking scheme. Here you are defining the interrupt scheme, arbitration scheme, your pin out of the device, and all those level of details. So, so from this step onwards, I mean, you have detailed down your product to a level that you can start putting together the RTL, right? So, so this is how you will progress, in your SOC design cycle. There are, if I just do a recap in, I mean, a couple of minutes, there are customer-facing marketing requirement guys, I mean, who collect the product requirements from market, at a high-level application language, and then there are architects who are translating the application language to, let's say, architecture specification or the product requirement specifications, and then there are other set of people who comes into picture, who you call as a design implementation folks or the SOC architects, who will translate, I mean, the architecture specification to detailed design technical specification, which can now be translated into. Okay, so moving next, so this is, I mean, just one typical block diagram which may come up, I mean, through all the steps, which we have seen in the previous slide. So in any typical SOC, you may have a core. So so let's say here we are showing PowerPC as one core there. There would be an interconnect, the crossbar switch, the core and the multiple peripherals, accelerators, and masters and slaves, will be sitting on this crossbar. You can see, let's say, the DMA switch is DMA sitting there for direct memory access, which will be used to transfer, the chunk of data from one memory location to other memory location, either within the chip or outside the chip as well. Then basically, you will have, let's say, debug interface provided here like JTAG. Then you will have, let's say, I mean, there could be embedded memories you were talking about. So let's say in this chip, you have an embedded 4 meg flash here and 256K SRAM here. So this is a place, where you may either burn a lot of some of your program code, or you may be, when you are doing a DMA, you may be transferring the chunk of data from external world to your internal embedded RAM and do a processing here and then take the data out. And then I mean, you will have let's say a lot of interfaces which goes outside the chip, depending on the application space, right? So here you have let's say DSPI interface, ADC interface. Then you have analog muxes. I mean, let's say there are 4 ADCs, but at a time you want to show only one ADC visible to the external world. So you may have an muxing mechanism present there, so that you can leverage the internal hardware to the maximum capacity, but you optimize the number of pins, which are going outside the chip, right? So, and this is just a simplistic block diagram, but there will be many other things, in a typical SOC block diagram, let's say, for the system level clocking or arbitration or some of the other functionalities. But this was just to give you guys a flavor, I mean, how market to product requirement to architecture definition to detailed design technical specification, and end of the day, what you might get, which is now translated into RTL from here onwards. Okay, so now you have, let's say, your block diagram for your chip ready, and you want to put together the RTL for your design, and RTL could be in any hardware description language, Verilog, VHDL, or a combination of them. Okay, so so when you are putting together an RTL, imagine, I mean, today, we are working on SOCs, which may be more than 100 million transistors, right, in a chip. So no one will do each and every line of RTL code from scratch, when they are building a chip which are 100 million transistors, and time to market is very, very important. So what ultimately happens is there are some standard functionalities which are carved out from the silicon, and those standard functionalities are the basic building blocks which can be reused, from one SOC to other SOCs. And these reusable building blocks, in simplistic terms, can also be called as IP blocks. So you can imagine, let's say in your SOC you need an Ethernet interface, but there could be 7 other products you are doing in parallel, which again needs the Ethernet, right? So there is no fun that those 10 people, in the same company doing the Ethernet 10 times. So you can build Ethernet once, and then those 10 products could be utilizing the same Ethernet module in their own product. So that is just one example of what IP blocks may look like. So these are generic functional blocks with defined interfaces which can be reused across multiple ICs, catering to totally different application domains. It can be digital, analog, or mixed signal IPs, right? So digital, like Ethernet block I mentioned. Analog, let's say in PLL. Mixed signal IC, let's say an ADC subsystem, which could be taking the world from data from external world in an analog format, and then doing the conversion, in the digital world, and then feeding, the data to other components in an SOC for further processing. Okay. So so we talked about IPs. So what does really IP mean? So when you are building the SOC and you are doing an IP, you have to build the IP in such a way that when these IPs are stitched in a higher level abstraction, which is SOC, it should be seamless integration, right? And to facilitate that seamless integration, there are certain set of deliverables, which IP providers will need to enable to the person who are working at a next level abstraction level. And these are those set of deliverables. So one is a stub. So stub is nothing but defining the pinout, of the IP. RTL is the actual functionality. Functional pattern. So whosoever is doing the IP, so he will verify that IP in isolation using certain set of functional patterns, and he will also enable those functional patterns for next level abstraction use. If a person wants at a next level abstraction, he might utilize similar functional patterns, massage it a little bit, and run the similar pattern at next abstraction level as well. Synthesis scripts and constraints. So ultimately, someone will need to translate this RTL into a gate level netlist, and to enable the gate level netlist, there will be certain clocking definition, some constraints in terms of input delays, output delays, or certain timing exceptions in terms of one of the signal may take 2 cycles to reach from source to destination. There are multiple clocks. There are no interaction between 2 clocks, so you need to define all those relationships, in the form of certain constraints, which the synthesis engine, will ultimately take as an input and give you a relevant gate level netlist. And last but not the least is the integration guide, which is a supporting documentation, which will help the SOC person to integrate the IPs in his own way. So, so this is just a very, very simple example. Let's say for encounter, the stub. Let me just take a laser pointer if I can. Okay, so on the left side is the stub model where we are defining only the pinout of the IP. IP is counter in this case, and when we are looking at the actual RTL, we are not defining only the pinout but the internal complete functionality. So, so what else is needed to build the chip top RTL model? Let's say now you have the bunch of IPs available with you, which are representing the generic reusable functions. So other than that, each chip will have its own way to interact with the external world, right? Let's say one chip may have Ethernet interface, other may have a USB interface, SD card interface, and similarly, there could be some analog interfaces going outside the chip. So basically, each chip will have its own I/O definitions, and so your chip top RTL model will need to define, your interface of the chip, as it talks to the external world, and that's where the I/Os also gets integrated in the chip, because I/Os are special functionalities, which usually works at an higher voltage, and also, it has to really drive the larger load, outside the chip compared to the load, which the signals inside the chip may be carrying. Contains all the IP instantiations, so it's pretty intuitive. Contains the IP parameter configuration. So you can imagine when we are building the generic reusable IP blocks, one IP block may have multiple type of functionalities embedded in it, so that it is really reusable for multiple type of SOCs. But a given SOC may not really need all the functionality, and if they use all the functionality, then the gates needed to realize are too many. So IP will provide the enough parameterization through enough parameterization configuration, so that end SOC, the person who is building the end SOC, he can enable those parameters and customize that IP use as per his application. And then, of course, describes the chip connectivity, right? So when you are doing the chip top RTL model, so here you will define the complete connectivity between different IP PCs, IOs, clocking modules, your interrupt modules, your arbitration, your safety features, your debug features. So your chip top connectivity will ultimately define the connectivity for all these pieces. Okay, so once your chip top RTL is ready, so next step is how you next important step, in the design flow is how do I make sure that I really build what I wanted, right? So you achieve that by verifying your design. So what is a verification? So basically you have a design under verification here, and you want to exercise this design under verification, or sometimes you can also call it as DOT, design under test. You provide certain set of stimulus, and then you have certain expected, output from the device, and you measure the output, which is coming out from this device against that expected output. And if it matches, then that means, your RTL model is behaving as expected. And if there is a mismatch, then that means there is something to debug, some correction is needed in the functional description, and then you go through that cycle again. Okay. So so how a typical verification flow is represented? So basically this SOC netlist is nothing but the SOC RTL, which we discussed in last few slides, and in a pictorial view, SOC RTL is a combination of different IP blocks. The architecture specification and the pin muxes, which defines the external world interaction of the SOC, and then the SOC logic, right? SOC logic is something which is over and above the IPs. Your SOC clocking scheme, arbitration scheme, your let's say clocking debug scheme, safety scheme. So all those things kind of gets represented by this SOC logic, and all these things combined together ultimately forms an SOC RTL, right? So so what a verification team will do, how to make it testable, right? So so one thing first thing they will need to do is, let's say there are certain clocking features, or the reset features in the design. So how do you really exercise those clocking in the reset functionality? So they may have certain pin drivers. So these pin drivers are kind of enabling, providing certain stimulus on those pins, which are coming outside the chip, as a clock or reset. Then the BFMs. So you can imagine, let's say your SOC, these BFMs are bus function models. So you can imagine, let's say your SOC is supporting an Ethernet functionality, right? And you're trying to verify your design, and you are giving out certain outputs on an Ethernet interface outside your chip. Now, how do you measure that output? How do you make sure whether the output you are giving to external world is really compliant with the Ethernet protocol or not, right? So some of those intentions are met by using these box function models. So these are the soft components which are part of the test bench, and they represent the functionality of the devices which my SOC will talk to in a product world or in an application world, right? And then the monitors and checkers. So if you go back to the block diagram which we were seeing earlier, there is a crossbar, and the crossbar is connected to multiple peripherals, masters, and slaves. And each of those interface is supposed to be compliant to the protocol, based on which that crossbar is designed. It could be AHB or APB or any other crossbar interface. So these monitors kind of represent the protocol represented by those crossbars, and when any transaction is happening through that crossbar, for an example, and if that transaction doesn't really meet the protocol specification, these monitors will kind of throw an error, right? So you can imagine in a 100 million gate SOC, when you're doing the verification, I mean, you wrong. So these are the monitors and checkers, which will give you enough hints and the information that where things have gone wrong, in an SOC, and that will enable the verification engineer for the debug, and then get to the root cause and see, what change might be needed in either in his pattern or the RTLs. Okay. So having verified the SOC, next thing is DFT. So I may be going a little fast in the interest of time, so that we can cover the whole content here. So DFT is designed for testability. So what is testability? A design attribute that measures how easy it is to create a program to comprehensively test a manufacturer design's quality. So you can imagine, let's say again, same case, 100 million transistors, and each transistors having multiple nodes. And each of these nodes during manufacturing may really can, let's say, get stuck to, let's say, 0 or 1 simplistically, right? So now testability is an aspect that, how you can reach out to each of these nodes in your design, how you can control the stimulus going out to every node in the design. And if you are able to stimulate that node and you are able to capture the fault, how you can propagate the faulty output all the way to your chip IOs, right? So that's ultimately DFT is all about, making your every node completely controllable and observable. So that controllability and observability concept is kind of explained here. So let's say this is one 2-input gate and one output, and these are the nodes at some deep down hierarchy in an SOC. And when you trace the input cone and output cone through a lot of sequential and combo elements coming in the path, it will ultimately reach somewhere on the primary inputs and the primary outputs, right? So the testability is all about controllability. What do we really mean by controllability is, if I give some stimulus on this primary inputs, I should have a way that I should be able to stimulate this A or B in any fashion which I want. So that's what is meant by controllability. So what is observability? So if, let's say, I capture the output on this gate on Z output as 0 or 1, again there is bunch of logic, both combo and sequential coming in between, from the Z output to your primary outputs. So how am I able to take the faulty output from this gate output all the way to primary output? So that defines observability. So these are two very, very important concepts, controllability and observability, which defines how testable your design is. Okay. So DFT continued. So basically, what kind of faults, DFT or design for testability is trying to capture. So manufacturing issues. So you can imagine, the feature size is getting smaller and smaller. So manufacturing process is getting more and more complex. So so while, there are a lot of precision equipments used in the process, but there are always, certain possibilities of some manufacturing defects kind of creeping in. And the reasons for the manufacturing defects could be, let's say, contaminations causing the metal bridges. Metal bridges is nothing but a short, let's say, between two metal wires. Defects in the silicon bridges, photolithographic defects, oxide defects. So these defects will ultimately result in some shorts, or some of the nodes, remaining open. Some of the nodes, getting shorted, or one of the node is taking more time, to make a transition than what you simulated. So these are the end manifestation, this manufacturing defects may result into. So what could be the end result? Either the part is non-usable. Non-usable meaning you compromise certain functionality, or part works at a slower speed, meaning you wanted your part to work at 100 megahertz, but certain defects are slowing down the nodes, and at the end of the day, your chips works at a slower speed. Okay. And normally the DFT techniques which are used are for scan, memory bits, and JTAG. So I'll have 1 or 2 slides to introduce the concept of scan, which is kind of backbone of testability in all the modern day SOCs. Okay. So what is the scan all about? So I'm sure all of you have studied the D type of simple flip-flops, in your electronic courses in the colleges. D flip-flop a simple functionality. It's an edge triggered sequential element. So basically, a Q output follows the D with the every clock change, right? So how do I make this flop scannable? So in front of the D input, I add a mux, and I add a control signal which is called as scan enable. So when the scan enable is 0, my this D flip flop works at same as the D flip flop on the left side. The functional data gets latched in the flop, with the clock trigger. And when my control signal scan enable is high, at that time it's a scan data, which is captured by the flip flop, when the clock triggers, right? So you can imagine there is one mux added in front of the input of a flop, and one of the input now scan data is in your control, and the another input to this flop is a functional input, and so this is how it is shown, in the below waveform as well. Okay. So how this helps? So this is how it helps. So let's say, this is a simple design before any scan session is done. So let's say this is a primary input, this is a clock and reset, and these are the multiple outputs, which are the combination of different Q and the QZ values of flops sampled and then combined with some combo logic. They are translating into these 4 outputs: output 1, 2, 3, 4. So what happens when you make it scannable? So now you can see there are 2 more control inputs added, which are SD and SE. SD is a scan data, and SE is scan enable. So these are added to all the 4 flops. Scan enable input of all the 4 flops are shorted, and the connections are done such that the SD input of one flop is connected to Q output of previous flop. So you can see this line where my laser pointer is moving. Q output is connected to SD input here. Q output of second flop is connected to SD input of third flop. Q output of third flop is connected to SD input of fourth flop. So we call it as a scan chain. Now basically these 4 flops are connected, one after the other, and the output of one flop is feeding the scan data input of the next flop. So let's see how it helps. Okay. And end of the day, you have one scan data in, which is feeding the first flop, and one scan data out, which is which is connected to the output of the last flop in the scan chain, and in between the flops are connected back to back. So let's say how this connectivity helps. So how scan works? Okay. So so let's say at my first clock edge, my scan enable is high. So as I explained earlier, when my scan enable is high, all the flop that mux is programmed such that the data flows through SD input. Okay. So the flop will capture the data through SD input. So let's say my scan in is 0. So as my next clock comes, the 0 goes on, from let's say first flop to second flop. At the next clock edge, 0 propagates to third flop because scan enable is high and all the flops are connected back to back, Q to SD connections. And you can also visualize that, I'm giving different inputs on the scan in, through the external world. So let's say next clock comes. So the one which was available on primary input on the previous clock edge, that goes to the next sequential element, and the 0 propagates further. So now, after let's say 4 clock cycles, I have been able to condition all my flops to some desired state, right? So once I have conditioned all the flops to my desired state, what I will do is I will bring the scan enable low. So when I bring the scan enable low, what happens is now all the flops will be capturing the data through their D input, right? So I condition all the flops to some desired state. Now this combo logic evaluated its state based on the desired values which are deposited in those sequential elements, and depending if there is faulty circuits somewhere in this combo cloud, that particular node will not give a desired value, and that value now shows up on the D input of these flops. And when I give next clock edge, what happens? These flops will capture the value which is coming through the D input, right? Because my scan enable is low. So with this clock edge, all the flops will capture the actual state from the combo logic. So again, I will make the scan enable high, and I will start shifting out the data through these 4 flops to the primary outputs. So all after the 4 clock cycles, the state of 4 flops is available outside, And now I can compare the the state of these 4 flops against what should have been the correct state, and if there is any mismatch, then that means some of the circuit has gone wrong inside the chip. So the scan is a very popular technique using which we are able to make every node in your design completely controllable and observable. Okay. So this is just another slide, how DFT fits in the flow. So there is a functional RTL code. You go through the logical synthesis, you translate it in a gate level netlist, and then you do a scan insertion. Scan insertion is nothing but converting your normal flops, to scannable flops, and then building a scan chains. Connecting one flop to other flop, and this is what we call as an scan gate netlist, and then ATPG and PG is an automatic test pattern generation tool, which will evaluate the booleans of the combo logic and will determine what set of inputs you should provide to the primary input to exercise all the faults. And this ATPG tool will, at the end of the day, will give you certain set of vectors, and these vectors will go for the verification, and the same vectors will go to the test engineering team. So when your silicon comes back, they will run the same scan vectors, and if any vector fails, then that's how they are able to figure out, any manufacturing defect which has creeped into your design. Okay. So after your DFT is done, next is physical design. So now let's say you have done your functional RTL coding, you have added the test functionality to it, you have verified your design for testability and the functionality. So now you are ready to translate your RTL to a gate level netlist, which can be taken in a physical design. Okay, so now we have few slides coming from here onwards, which talks about the physical design process. So what happens in the physical design process? Typically, you have a chip top gate level RTL, and then floor planning. You will do the physical synthesis. So which is, you translate your gate level netlist, which is physical aware as well, so that it can infer the right size gates, right size buffers, as signal travel from one place to other place. You will connect, all these gates with another in the routing step. Then you will do the parasitic extraction, all the parasitic resistance and capacitance associated with those routing layers. Then you will do some singular integrity checks. You will do the static timing analysis, some physical checks and tape out. So we'll talk about all these aspects, in the next few slides. So hierarchical floor planning. So depending what kind of chip you are making, it could be a small chip, which is a couple of million transistors, to a large chip of 100 million transistors. So different type of floor planning techniques will be used. So this is one way where you are doing more of an hierarchical floor planning, where it is impossible to do chip as a flat implementation. So you will carve out different blocks in the floor plan. So you can imagine it's doing a floor plan like your house. So you will figure out which are the talking blocks, which blocks needs to be sitting close to each other, which are the blocks which are noisy and needs to be isolated, which are the blocks which are IO intensive and they should be sitting near to the IOs. So a lot of those considerations, will go into building the floor plan, and all these different colors are showing, the different physical partitions, which you have carved out from the chip. So different people may be building these physical hard macros or the physical partition, and someone will stitch all these physical hard macros together to give it a shape of chip top, to give it a shape of, a chip top model in a physical world. So at the same time, you might be doing some of the other associates which are smaller, and you don't want to incur the penalty and complexity of hierarchical design. So you may have a very flat approach where you have some hard macros, which are the analog blocks, let's say some PLLs or ADCs or IOs, but beyond that, you are implementing the remaining chip as a flat sea of gates. Okay. So once you have the floor plan, next what you do is physical synthesis. So synthesis is nothing but translation of your RTL model to gate level netlist. And when you are doing the synthesis, you are trying to optimize your design in 3 different dimensions. You want to get the minimal footprint in terms of gate area, because bigger the netlist, bigger is the layout, more money you pay to the foundry for every part fabrication. Second one is power. So you want to realize gate level netlist so that the power remains minimal. That is more for that is both for efficient package design, low cost package design, and also I mean, the customers are very, very sensitive about the power consumption, because that's how they will at the application level, I mean, different components will add up to their application level power footprint, right? So there are certain specifications coming from their standpoint. The third one, last but not the least, is performance, right? So your design has to work at certain clock frequency. So your synthesis step has to meet, I mean, all these three competing requirements, while generating a gate level netlist. Okay, once your gate level netlist is done, next thing is standard cell placement. So Vedanta talked about PDKs. So the people who are providing the process design kits or the digital design kits, they will already be giving you certain standard cell libraries, and not every SOC person will do the every standard cell design, from scratch. So he will use the pre-built, standard cells, and those standard cells are capsulated in certain library formats. Let's say, I mean, the left and the def library exchange format, design exchange format that defines the physical view, and then synopsis, let's say, I mean, liberty formats that defines the timing view or the power view of these standard cells. So this goes as an input to synthesis tool, and ultimately synthesis tool will give you the netlist, and once you place, this is how the view might appear. So each standard cell will have the similar height, and these are arranged such that the VDD and the ground rails of these standard cells align with each other, and they are connected to the chip level power and the ground networking. Okay. So once, let's say, a placement is done, next step comes, I mean, the routing. So basically now you want to connect the different pins, of the standard cells with each other, and that's where the metallization comes into picture. So this is just a simplistic view. So you can imagine this this view geometry is the, let's say, probably the VDD or the ground rail connecting the different different standard cells VDD rails together, and then you are connecting the pins, of one standard cell to other standard cell, and these different color geometries, let's say blue to red. This is where the layer hopping is happening, and wherever there is a layer hopping happening, the vias will be coming into picture, which is making the physical contact between upper and the lower metal layers. Okay. So as you are done with the layout, you had the base devices done, then you have the metals, laid out on top of your chip, connecting different nodes. So so all these metals are and the base layers are interacting with each other, I mean, an electrical world, and there are some parasitic associated with this. So this is again a simplistic view. Mn is let's say nth layer metal layer. A signal is, let's say, I mean, laid out on Mn layer. Another signal which is laid out on Mn minus one layer, one level below. And these will, I mean, interact with each other electrically. Electrical, I mean, electrical lines, will electrical field, will couple these metal plates in multiple different ways. So again, your these are the concepts which are there in your theory classes as well. So R will vary with W and T. So you make the wire thicker, and the wider, it will be able to carry more current. Similarly, I mean, the overlap capacitance will vary with the height, width, and dielectric constant of the insulator which is coming in between. And then, these metal wires will couple through the side walls as well. So that's what will result into coupling capacitance between different metal layers as they are running parallel to each other. Okay. So both CC and CC varies with inter and the intra layer dielectric constant. So, but obvious, I mean, higher the dielectric constant epsilon, I mean, more will be the capacitance. Either the intra layer through the sidewall coupling, or I mean, or the electric field interactions between the layer above and below. So once, I mean, you have let's say the gate level netlist, and you have the parasitic information, and you have defined, that's where now the static timing analysis comes into picture. So what happens in static timing analysis is you define the timing specification. Let's say, I mean, I support an Ethernet interface to the external world. So so when I give any signal to external world on Ethernet interface, I can consume only specific amount of time within the chip, right? So the remaining part of my clock cycle, I have to leave for the external device. So similarly, when signals are interacting from one physical partition to other physical partition inside the chip, again we will define the input and output timing constraints so that everything adds up together and makes one clock cycle. So we'll define the clock cycles. I mean, in the complex SOCs, clocking definitions could really be very complex. This is a design netlist, which is the gate level netlist out of your after your routing is done. And then your technology rules and circuit library, which defines how much delay will be consumed when any standard cells makes a transition from state A to state B. And so all those inputs will go to a static timing analysis tool, and this tool will tell whether you are able to propagate a signal from, let's say, place A to place B in an allocated time or not. If not, then basically there will be the feedback loops back to the netlist. You do the improvisation there till really you are able to propagate the signals in desired time from your source to the destination. Okay. So once your timing is complete, then you want to do some physical design rule checks. So again, I take a reference of physical design kits, which was introduced by Vedanta. So he mentioned a word, keyword there, DRM, which is Design Reference Manual, right? So each foundry will represent a set of rules associated with different mask layers in DRM, Design Rule Manual. And the people who are doing the PDKs, they will translate the design rule manuals in an tool understandable decks. We call it as a deck. The DRC deck, and this DRC deck will define, for your design to be manufactured correctly, what rules when you will need to obey, when you are doing the layout of your design. So one typical example is, let's say, 90 nanometer. So metal to width must at least be let's say 0.14 micron. So if there is any metal which is less than 0.14 micron, then the EDA tools will capture this as an error, and you would need to correct it. Otherwise foundry will not accept this data. So similarly, there are many other rules which are associated with one layer or interaction of multiple layers, which will define the overall DRCs. So last one is LVS. So LVS is layout versus schematic. You had a gate level netlist coming as an input, and you're going through complex, processing steps all the way from synthesis, then placement, clock tree synthesis, routing, and timing analysis. So there are all possibilities that end of the day your layout doesn't matches with your gate level netlist. So this layout versus schematic is a design flow step. Which helps match your golden netlist, which went as an input in your physical design process against, the netlist which came out, as you exited your physical design flow steps. It will compare those two spice netlists and tell, if these are matching or not. If they are matching, then that means nothing has gone wrong in the physical design process. So once, let's say, the physical verification steps are done, so we go to packaging, and then post-silicon test and validation happens. So these are the similar things which were introduced by Vedanta as well. So this is the automatic test equipment, where the purpose is to figure out all the manufacturing defects using the scan vectors which DFT team provided. And on the right side is a post-silicon validation, where you have your silicon, connected with other devices, which your silicon will talk to in an application environment. So here you are actually doing a functional test of that. Okay. So here this is good for I/O, AC characterization and manufacturing test, and this one is used for silicon validation is used for logic issues and bug. So similarly, these are the general test practices. So once, let's say, this is your wafer, typical wafer, and multiple silicons are manufactured here. So some level of test you will do at the wafer itself. So we call it as a wafer prover. Faulty dies are marked out, as this red process, and the good dies are taken out. So they are packaged, and the package device goes to the testing mechanism before silicon goes out to the customer. So this is just, showing certain targets of validation that in the functional world, you are doing the functional bug hunting, analog characterization, then some benchmarking for applications and performance. And I think with this we come to the end, about how the overall SOC design flow process looks like. So we have a couple of conclusion slides here. So I'll probably request Vedanta to maybe take over from here and walk us through the conclusion slide.
Sure, Sham. Again, thanks a lot for this great, insightful deep dive on various topics. I think I just have one slide, and also we'll have some 10 minutes of Q&A. So maybe you can move directly to the last slide. So, guys, as you saw, right, we just built a storyline right from the context setting of what is the value chain in this industry, how each role plays to its own merit, and how many opportunities you have, whether it is in the PDK side, full custom, analog, digital. RTO to GDS side or packaging and test side. So immense opportunities ahead. But I think as a summary, if I have to give you a few takeaways that you can take home, is that SOC Design Flow will continue to be the cornerstone or the backbone for our design effectiveness and efficiency. And if we continue supporting the industry value chain that we talked about for all the product development, it is the key that will propel all the industry trends, all the jargons that you that you hear, whether it is the Moore's law technologies going in, or the AI ML progression that is happening, or autonomous driving, IoT, etc. And it will be the differentiator. Companies and organizations or institutes that are able to do effective designs, SOC through the right design methodology, will have the competitive advantage of having the best-in-class power performance area, as Shyam was talking about, or safety compliances, security, robustness, and reliability. So this is our cornerstone of making great designs, I would say. So bank on this point. Then again, this is a shout out to all of those who are on this call are students and who are aspiring semiconductor professionals or fresh engineers. I think there are vast opportunities, as I said, whether it is from a rules point of view. I will not read out all the words I have spoken multiple times, or specialized expertise areas. Right? I think this is the era of specialization. It is good to be a generalist, but once you have specialization on these various domains, I think that really gives you a great performance stage. And finally, since this webinar series is also about inspiring skill development for great nation building, as our leader Sanjay keeps saying, I think this is what inspires all of us and should inspire all of you to clarify your fundamentals, to make your fundamentals so strong, whichever subjects you are reading, whether it is analog design, digital design, microprocessor design, device electronics, circuits. I mean, have your fundas clear, number one. Number two, get an opportunity, whether it is through your institute labs, to work on various tools, and also through your internship with your various companies or other organizations, or of course, if not, at least on the when you are fresh joining the job world or doing your advanced research, whether it is PhD or postdoctoral. I mean, try to get a hold of all these Western-class tools which are listed here. I mean, this list is not exhaustive. I've just picked up a few names, not that we just have only these names, but okay, this is not an exhaustive list. And last but not least, also about how do you build in automation by mastering the right skill sets on whether it is Unix, shell scripting, Perl, so I think on these three vectors we will conclude. But before we open the Q&A session, which for the next 7-8 minutes we can discuss, I think one note that I would like to leave this all with is the best time to be a young engineer in this field of semiconductor design. So give yourself a pat on the back that you are right in time. Do not worry about all these COVID-related delays which we are seeing. We are all going through some lot of pain, both on the personal side as well as professional side. I think it is a test of time. Just stay put, stay hold, and I think just keep your viewpoint on the long-term horizon. A lot of opportunities to really leverage. So I think wish you all the very best, and let's have a quick set of question answer round.
Vedanta ji, thanks a lot for your efforts. And I think my young innovators in the campuses are excited with this first session. Although this is an introductory session on the SOC design flow, but yes, a lot of queries. Guys are very excited. So my request to all of you, my young innovators, we have an email ID. Please note down that nxp_campus_connect@NXP.com. Our experts will reply on all those queries. Will answer all your queries, and we are always ready to support you during your journey. And our Prime Minister goal is Atmanirbhar Bharat, and our Atmanirbhar Bharat is, totally dependent on, us. So it is our roles and responsibility to innovate the things, and NXP is ready to support you at every stage. This is the message from our country head, that is Sanjay Gupta. He is very, very, aggressively supporting all these initiatives, and Vedanta is also, part of our ISA forum, where he is driving the Auto CIG group. So a lot of innovations going on, and yes, we are committed to support you on that. Just note, we are closing today's session, and thanks to all the attendees, my dear young innovators. We are also excited with the numbers, and we are very hopeful that next time a lot more will be there. And the next track, this track is related to the VLSI. Next track is mainly related to the system engineering, where we are going to cover the things related to applications, software, systems, different types of use cases. So guys, a lot of excitement is there. You please share this message with your friends, professors, faculty members, researchers, and so on. And we are always ready. Use the LinkedIn page, join there, get the updated information there, and use our email ID. We'll support you through that channel. With that, thanks a lot. And we are closing today's session. Thanks, Shyamji and Vedantaji, for your time and effort.
Thank you. Thanks to all the attendees for staying put until this hour. And thanks, Manish, for the opportunity. Thank you, Shyamji, for being great. Thank you very much.
Yeah, thanks everybody. Thanks for giving this opportunity. It was nice interacting. Thank you.
Yeah, that's great. Thanks a lot, everyone. Okay, bye-bye. Thank you.
Bye. All the best.